Hello out there, welcome to this tutorial on binary operations. In this video, we'll be looking at closure property. First, we look at definition. Let A be a non-empty set and X and Y be elements of set A. We can define a rule combining the two elements X and Y as X asterisk Y is equal to Z, where asterisk can be any or combination of arithmetic operations and Z may be an element in A or not. This rule of combination is called binary operation. If Z is an element in A, then A is said to be closed under the binary operation asterisk. So we now look at some important set, starting from the set of integers. The set of all positive and negative whole numbers, including 0, is called the set of integers. It is denoted by Z. Is Z closed on addition, subtraction, multiplication, and division? So we'll now take a look at that. Then for addition, if we pick two integers and add them, will it give us integer? So we pick the first number to be 2 plus the second number to be -3. So 2 plus -3 gives -1, and -1 is an element of Z because -1 is an integer. So we can say now that addition is closed on integers. Then for subtraction, we pick another number which is 5 minus 3, which is also an integer, and 5 minus 3 gives 2, and 2 is an element in Z since 2 is an integer. Then for multiplication, we pick two integers, multiply them, and see if we will get integer. So we pick 3, multiply by -2. 3 times -2 gives -6, and -6 is an integer. Therefore, -6 is an element of Z. Then for division, we also pick two numbers, divide them, and see if we will get an integer. So we pick 6 divided by 4. 6 divided by 4 gives 1.5, and 1.5 is not an integer. Then we now write 1.5 is not an element of Z, which means Z is not closed on division. For your information, there is restriction to this. If the divisor is a factor of the dividend, then the quotient will automatically be an integer. So we need to verify with as many numbers as possible, and your choice of numbers must be carefully selected so that you not keep picking the divisor to be a factor of the dividend, which will give the quotient as integer. So we now make our conclusion that the set Z is closed under addition, subtraction, and multiplication, but not closed under division operation. So we are done with that for integers. We now go for natural numbers. The natural numbers. The set of all positive whole numbers, which may include 0 or not, is called the set of natural numbers. They are also called counting numbers. It is denoted by n. Is n closed on addition, subtraction, multiplication, and division? So for addition, we take two natural numbers, add them together, and see if we get natural number. So we pick 5 plus 8. They are both natural numbers. 5 plus 8 gives 13, and 13 is also a natural number. So it is an element in n. For subtraction, we also pick two natural numbers, 3 minus 5. 3 minus 5 gives -2, and -2 is not an element in n, so it is not a natural number. We cannot count an object and record -2, so 2 is not an element in n. Then for multiplication, we have 4 multiplied by another counting number or natural number, which is 2. 4 times 2 gives 8, and 8 is an element in the set of natural numbers. Then lastly, we pick division. 9 divided by 2. 9 divided by 2 gives 4.5, and 4.5 is not an element in n. So we cannot count an item and say we have 4.5, which is not possible. Please be informed in the subtraction here. If you take 3 away from 5, you are likely going to have a positive number, which is a natural number. So we have to consider all possibilities. Again, we need to be careful here also. We should not take the divisor to be a factor of the dividend. Otherwise, you are going to have a whole number as quotient, which will fall into the set of natural numbers. So we now conclude. In our conclusion, the set n is closed under addition, you can see, and multiplication, but not closed under subtraction and division operations. So that is that for natural numbers. We go for the rational numbers. The set of all numbers that can be expressed as p over q, where p and q are integers and q is not equal to 0, is a set of rational numbers. It is denoted by q. It should be noted that all integers are rational numbers, since 6 can be written as 6 over 1 and -2 can be written as -2 over 1. Is q closed on addition, subtraction, multiplication, and division? For your information, since z is a subset of q, we just established here that all integers are rational numbers. Therefore, z is a subset of q, and z has been established to be closed on addition, subtraction, and multiplication. We shall only test for division. So for division, if we have 2 divided by 7, that will give us 2 over 7. So it is in the form of p over q, where p is 2 and q is 7. So this 2 over 7 is an element of rational number. So we now conclude that the set q is closed under addition, subtraction, multiplication, and division operations. So that is all for the rational numbers. So we go to the next set of numbers, the irrational numbers. If it is not rational number, it is then irrational numbers. So we now look at the set of all numbers that cannot be expressed as p over q, where p and q are integers and q is not equal to 0, is said to be the set of irrational numbers. It is denoted by r \q, that is removing the rational numbers from the real numbers. Then we'll be talking about the real number shortly after this. So we now look at some categories of numbers that are irrational numbers. So we have pi, the Euler's constant, which is e square roots of positive integers that are not perfect squares. are irrational numbers. So we should note that this set of irrational number is closed under addition, subtraction, multiplication, and division. Add any two irrational numbers, that is pi plus pi will give us pi. So pi minus the Euler's number, for instance, will give us an irrational number. Then their multiplication will still be an irrational number, their division will still be an irrational number. Then we now go to the next set of numbers, and that will give us the real numbers. The set of all real numbers comprises of all integers, rational and irrational numbers. It is denoted by R, and we should note that the set R is closed under addition, subtraction, multiplication, and division. Since integers are closed under addition, subtraction, and multiplication, and rational numbers are closed on all of the four operations. Therefore, we conclude that R is closed under addition, subtraction, multiplication, and division. Now, from here, we go into solving some problems with respect to closure property with a defined operation. So we start with the first problem. Problem 1. The operation is defined on the set Z of all integers as x operation y is equal to 2xy minus 3 for all xy in Z. Is the operation closed on Z? We have established at the beginning of this video that addition, subtraction, and multiplication are closed on Z. If you look at this operation as defined, this is multiplication and subtraction. So we can see now that the operation is closed on Z, but we need to verify that. So in our verification, we just choose values for x and y, then operate it based on this operation and see we are going to have integers all true. So we let x be equal to 3 and y be equal to 4, where 3 and 4 are integers. So 3 operation 4 will be 2 times 3 times 4 minus 3. This is going to give us 24 minus 3, which gives 21, and 21 is an integer. Then we pick another set of numbers. So we let x be equal to 2 and y be equal to negative 1. So we now say 2 operation negative 1 will be 2 times 2, this 2, then times negative 1 minus 3. 2 times 2 gives 4. 4 times negative 1 gives negative 4 minus 3, and that gives negative 7. And negative 7 is an integer. Then we take our last set of values. We let x be equal to negative 5 and y equal to negative 3. We have stated in the beginning that in order not to leave out anything that will affect our result, we need to try various form of numbers within the set. Like here, I have picked the first number to be odd and the second number to be even. Here is even and negative odd numbers. Here they are both odd and they are both negative. So we now operate them. That is negative 5 operation negative 3 will give us 2 times negative 5 times negative 3 minus 3. So this cause is basically substitution. So 2 times negative 5 gives negative 10. Negative 10 times negative 3 will give us 30, then minus 3 will give 27, and 27 is an integer. So we have shown now that Z is closed on the given operation. So we now conclude Therefore, the operation is closed on Z. That's all. Then we go to problem 2. The binary operation asterisk is defined on the set R of all real numbers as x operation y is equal to x squared minus 2y for all xy in R. Find A, 3 operation 4, B, negative 2 operation 5, C, negative half operation half. Is the operation closed on R? Then we start with A part of the problem. 3 operation y, it means x is equal to 3 and y is equal to 4. So we are going to have it as 3 squared minus 2 times 4, and that will give us 9 minus 8, which is equal to 1. And 1 is an element in R, since 1 is a real number. Then for B, negative 2 operation 5, which means x is negative 2 and y is 5. So we substitute in here. So we have negative 2 squared minus 2 times 5. Negative 2 squared is 4 and 2 times 5 gives 10. So we have 4 minus 10, which gives negative 6. And negative 6 is still an element in R. For C, we have negative half operation half, so which means x is negative half and y is half. So we substitute in here. We have negative half squared minus 2 times 1 over 2. Negative half squared is 1 over 4 minus 1. 1 over 4 minus 1 is going to give us negative 3 over 4. So, and this negative 3 over 4 is still an element in R, since negative 3 over 4 is a real number. We can now make our conclusion that from A, B, and C, the operation asterisk is closed on R. We can all see that the operation, the various values of real numbers used and substituted into this operation all give real numbers. So we go to problem 3. For problem 3, the operation dot is defined on the set Z of all integers by x operation y is equal to xy minus x over y for all xy in Z. Is the operation dot closed on Z? By inspection, we can easily see that the operation is defined on 3 operations. We have multiplication, subtraction, and division. So you can see from the beginning of the video, we have established that division is not closed on the set of integers. So we can conclude from here directly that since the operation contains 3 operations such as multiplication, subtraction, and division, therefore the operation dot is not closed on Z. But to show that, we just get values for x and y, operate it, and conclude. So we now let x be equal to 2 and y be equal to 3. Since it involves division, our choices for x and y will be selected carefully so that they are not factors of each other. So with this, we now say x is equal to 2 and y is 3. We carry out 2 operation 3 so that we now have 2 times 3 minus 2 over 3. 2 times 3 gives 6 minus 2 over 3. That's going to give us 5 whole number 1 over 3, which is not an element of Z, because 5 whole number 1 over 3 is not an integer. Therefore, the operation dot is not closed on Z. and that is the highest we are going to take in this tutorial. Please check the description section of this video on our YouTube channel to get the link to the playlist containing all the videos on binary operations. Please remember to like and share. If you have not subscribed to our channel, do so. Until we come your way again, goodbye.